plasma, QGP, is a remarkable state of matter created in laboratories through the collision of heavy nuclei, forming a QGP fireball. This exotic substance, believed to have existed microseconds after the Big Bang, undergoes a complex transition into hadrons, particles composed of quarks. Understanding this transition and the role of quantum chromodynamics, QCD, is a key focus of contemporary research in nuclear physics. The process begins with the collision of heavy nuclei, generating a QGP fireball. This fireball, governed by hydrodynamics, expands and cools. Hydrodynamics, which describes the behavior of fluids under various conditions, helps scientists understand the evolution of the QGP fireball. As the fireball expands, it eventually becomes too diluted for hydrodynamics to effectively describe it. This signifies the stage of hadronization, where the QGP transforms into hadrons, such as protons, neutrons, and pions, made up of quarks. The hadrons freeze out, preserving information about the final hydrodynamic state and allowing detectors to capture details of the collision. The challenge lies in extracting meaningful information from the experimental observations of these collisions. The maximum entropy principle plays a crucial role in bridging the gap between experimental data and the hydrodynamics of the QGP fireball. It provides a method for interpreting fluctuations in the number of observed particles, offering insights into the characteristics of the QGP. Recent research has introduced a novel approach to computing observable fluctuations in the QGP, enabling the identification of hints toward a critical point in the QCD phase diagram. This critical point is a significant yet unresolved aspect of quantum chromodynamics, describing the strong interactions between quarks driven by gluons. Simulations now allow researchers to study fluctuations in the QGP and use freeze-out to detect indications of this critical point. The connection between fluctuations in hydrodynamics and observed hadron fluctuations is crucial for mapping the QCD phase diagram. Large event-by-event fluctuations in the QGP are considered indicative of the critical point. The Run I-Beam Energy Scan (BES) program at the Relativistic Heavy Ion Collider (RHIC) has provided data hinting at the presence of this critical point. To pursue this lead, researchers at the University of Illinois Chicago proposed a universal approach based on the maximum entropy principle. This approach efficiently addresses challenges encountered in previous attempts, preserving all information about the fluctuations of conserved quantities described by hydrodynamics. In summary, the journey from Quark-Gluon Plasma to hadrons involves the collision of heavy nuclei, creating a QGP fireball that undergoes hydrodynamic expansion and cooling before transitioning into hadrons through the process of hadronization. The maximum entropy principle serves as a crucial link between experimental observations and the dynamics of the QGP. Ongoing research focuses on utilizing simulations to understand fluctuations in the QGP and detecting hints of a critical point in the QCD phase diagram, with experimental data from the RHIC providing important clues. The proposed universal approach based on the maximum entropy principle offers a promising method for translating hydrodynamic fluctuations into observable hadron multiplicities.